All right, so I'm pleased to introduce Sam Rubenzer, PESE, and owner of Force Consulting in Eau Claire, Wisconsin. Sam has 18 years of experience with structural engineering. Early in his career, he worked as a structural engineer for design firms in Minnesota and Wisconsin, collaborating on a wide variety of structures, including several years designing load-bearing masonry retail stores in a number of states. Sam also spent 5 years at RAM International and Bentley Systems, providing training to structural engineers on how to use STAAD Pro, RAM Structural System, RAM Elements, RAM Connection, RAM Concept, and other structural design tools. Sam started Force Consulting in January of 2010 and continues to assist fellow structural engineers with designs on a variety of projects, building types, and uses of software programs from Bentley, Riza, Tekla, IES, SCIA, and others. Sam has also been the structural engineering consultant to the Wisconsin Structural Masonry Coalition since 2010, and in addition, he works with the Illinois Structural Masonry Coalition too. Sam is an expert in structural software programs and has been a speaker at several national structural engineering conferences on the use of software programs for the industry. One of the topics Sam focuses on in his structural masonry analysis and design. Sam has a Master's of Business Administration from Marquette University and a Bachelor of Civil Engineering from the University of Minnesota. Sam is a licensed structural engineer in the state of Illinois and a professional engineer in many of the Midwestern states. And without further ado, here's Sam.
All right, so what we're going to talk about today is masonry movement joints. You guys have probably talked about or thought about movement joints. A bunch of different things here. So learning objectives, learn a little bit about movement joint definitions. And if, again, you guys have probably seen a variety of these type of talks on from the architectural perspective. There's going to be some overlap, but again, I'm going to try to talk about why movement joints are important to engineers, why an engineer might say, no, we don't need any movement joints, or we need more movement joints, or some of those different things. So overlap, but then cover why it's important to engineers or how you can help them out. I know you guys love to help out engineers. Movement characteristics, movement characteristics of masonry materials and systems, movement joint purposes and locations. All right, and then knowledge to design and detailed movement joints and stuff like that. Okay, so again, we're going to cover those basics, cover what goes on in corners, both for structural and for a veneer. Talk about horizontal movement joints. I think that's a really good terminology. I think sometimes we get a little bit confused about what's going on with those horizontal elements. Effects for structural, and then the all-important when we have openings, and we have more and more and more openings. So how do we deal with these openings in an effective way? So movement joint basics. The biggest thing about movement joints, and this is hard to see and review projects, and we do that a lot for the Structural Masonry Coalition here in Illinois. But my company, we do a lot of consulting work in Wisconsin, in Iowa, in Kansas City, in New Jersey, and all kinds of different places. And when we do project and plan reviews, probably the most heartbreaking thing when I see when I'm reviewing the masonry details, well, there's a couple heartbreaking things, but one of them is when it has a note in there someplace about to indicate, movement joints just based on a code reference, right? What we really need to do is we need to be very specific about where the joints need to be horizontally, vertically on our drawings. And I think that needs to be, we really need to do a lot better with that. I mean, maybe in schematic design we can throw a note in there, but I even say then it's probably not a good idea. And the other thing about movement joints, a lot of times when we talk about movement joints, there's a difference between veneers and backups or CMU veneers, structural veneers. So I'm going to talk about those before we get even deep into any of the pretty pictures that I have for today. So the vertical joints that we have, they're needed to prevent cracking. Anytime that we have a veneer, obviously what we're trying to do is provide a plane within a wall that's going to be where the wall is going to be able to move, right, without forming its own movement joint. That's what we're trying to prevent by putting these joints in there. So we're trying to prevent that undesirable cracking by putting in this purposeful, essentially, a crack in the wall. Needed when there's a differential support. Sometimes we have, again, different conditions where we have veneers that are kind of spanning over different types of elements structurally. Sometimes there's differential support in how we support those veneers. So there's another place where we want to put a joint. And then rarely, if ever, would you ever want to eliminate a vertical joint in a veneer. So I'm going to talk about when we maybe want to eliminate some of these vertical joints, but I'm not talking about veneers, right? Okay, horizontal joints in a veneer, it's allowed, therefore allowing differential movement, and that's not the same as differential support. Differential support is going to be for when I have a veneer that's in an elevation, it's maybe got two different elements supporting it, right? Maybe one's a foundation, one's a beam, as we kind of go on a slope site or something like that, right? So differential movement, what I'm talking about is the actual veneer and whatever it's holding, giving it its support. A lot of times that support is going to be moving vertically. It's going to be settling, especially if it's, and I apologize for any wood people, but if it's an inferior material, right? I mean, wood is, it's not used because it's superior to brick. It's used because it's available and all these other reasons. I'm not going to get into the wood thing, but it moves a lot, right? And so anytime that we want to do something with wood, or if we want to do something with steel, steel is also a more elastic material than you have with concrete and brick. And so differential movement, when we have wood or steel or something else backing up our veneers, that differential movement we have to think about, and that's why we need to consider horizontal joints. All right, the purpose is not to relieve, relief angles is something that people just, I know it's just casual, it's not a big deal, but it's kind of a big deal because it creates a perception. I don't know how many engineers have said, Sam, I think I need to relieve some of this brick. I'm like, no, you don't need to relieve the brick. And they're like, what do you mean you need to relieve the brick? There's relief angles that you have to put in. It says in this note, relief. It's not a relief angle. I mean, the brick can go, hundreds, thousands of feet high, right, without needing to be relieved. It's got lots of capacity. A lot of times it's going to be one of the stronger elements on the site. It's going to be able to support itself. So it's all about that differential movement between the backup and the veneer itself is why we need those horizontal angles. Some cases we can eliminate these horizontal joints, and I know there's very prescriptive places where we talk about in the code where they should have these horizontal joints, right? And so I apologize to you guys over here. I feel like if I turn this way, I might just knock everything out of whack. So I'm going to just focus on you guys. I'm going to ignore you guys for the rest of the day. All right. So in some cases, they can be eliminated. In certain situations, maybe it's a 36-foot high building. We don't need to put that horizontal joint necessarily at 30 feet. Or if it's multi-story and that horizontal joint is just, it's going to be hard to support the brick with whatever the substructure is going to be, at 30 feet. I mean, there's times where we can eliminate them, and it's very straightforward things to do. The code's meant there to put there to ease your designs, but sometimes you can go beyond what the code says prescriptively, and you can certainly eliminate those joints. So again, vertical joints, rarely to eliminate. Horizontal joints, we certainly can think about eliminating them. But this stuff is in the veneers, right? Because when I flip over to the structural, the backup, the CMU, the stuff that's behind it, or if it's a single white, then it's going to be all applicable. Vertical joints, again, needed to prevent cracking, right? We want to prevent the unintended cracks from forming in the wall, right? They can be used, vertical joints sometimes structurally are going to be added to isolate a certain element. I don't know if you guys ever do any design in a high seismic area or certain areas where you get into kind of specialty detailing for a shear wall element. And so that is not something you necessarily want to do for the entire structure. So sometimes vertical joints are more than just that thermal control that we need to prevent cracking. Sometimes we're trying to isolate an element from structurally so that we don't have to have all this special detailing for seismic response everywhere in a building. In some cases, we can eliminate them. And I think there's some cases where we absolutely should eliminate them from what I would say. When I say eliminate them, I mean from the kind of the standard prescriptive ways that you think about control joints. There's plenty of locations where we can move them, eliminate them, get rid of them. And in fact, I did a presentation a couple weeks ago in California, and they're like, well, of course you'd eliminate them. We have plenty of horizontal. Yeah, I mean, there's certain areas of the country where you just don't need horizontal or vertical joints in that structural wall. So what I'm saying here, in some cases, they can be eliminated for like the Midwest, for 90% of the country that's not California, right? A lot of times we just get into the mentality of we have to have these joints in it. We have to put them in. It's just what we have to do. There were so many problems when we didn't have those joints in it. Well, okay, yeah, common construction methods that are used throughout most of the United States and all over the world, you probably want to add them, but there's still certain situations where we want to eliminate it. And then the horizontal joints in structural, never and never and never. And I can't, sometimes I've seen this in a plan, right? And then I actually saw it in construction. So the really confusing thing to me is probably what you wanted to panelize was probably veneer. They didn't have that. They didn't have a horizontal shelf angle there, but they did for the structure, for the masonry backup. I'm like, well, this is not good. not anything that, because brick didn't need to be relieved. The backup, the CMU wall definitely doesn't need to be relieved for many feet high. 28 stories, 30 stories. We're talking about some high vertical masonry. So that's just, and again, I'm not sure why this happened. This is a bad design. It's I can't say anything about it in a good way, but I'm not sure why it got into this project, or that it's going to be common, or is that something that hopefully none of you guys ever see this. But if you do, this should raise some red flags because masonry just doesn't need to be relieved. Brick doesn't need to be relieved. We're trying to panelize these brick veneers and add these horizontal joints for specific reasons for how we're tying to the backup, right? And so the thought process here is, we're not tying to a backup. This is the backup, and this can support itself. And, it's just adding more and more weight, to the structure that's behind it. And just not something we want to get into. So in terms of isolating, those elements, and it's not just for those shear walls. I think that's a really easy example for us to think about, but also for partition walls. Partition walls within the current code, what the partition wall says, and I don't love the language. It says it's a wall that doesn't have a structural function. I'm like, well, but a structural engineer still needs to participate in the design of them because there's structural loads on this non-structural wall. But anyway, I think we need better terminology. It doesn't have a lot of load. It's got some, partition wall loads that are going to be applying pressure to it. If it's in a seismic region, it's got inertia forces due to its own self-weight that you have to resist and stuff like that. But partition walls, what the code is trying to say is, I don't want to get any unintended forces in there. I don't want to drag in some unintended shear load or vertical load into this element. It should be a relatively simple element. And that's why when we go into intersections, when we have an interior partition wall that's framing into an exterior wall, a lot of times it's a good place for a joint, right? Because it's just more complicated than it needs to be. And it's not a partition wall anymore if we suddenly have a hard joint there, create that T-section. Yeah, so it can be gravity, it can be wind, it could be seismic from other elements, right? It's seismic. In seismic events, it's got its own self-weight it's got to take care of, right? That structural load, even though it's a non-structural wall. And so this is what I would call the more common, right? Maybe we have a bearing wall or something like that where it's taking the out-of-plane pressure loads on the walls, but then maybe there's one element's taking the out-of-plane pressure loads and the vertical loads and the shear loads, and we have openings, and we have 24 inches past the edge of the openings that we have to take bars, and we have to have all this horizontal reinforcement in there because it's a specially reinforced masonry shear wall. It's kind of a big deal, right? But we don't want to do that every place. So sometimes we'll add control joints to isolate those locations. And so I say that, and I think I have to put this little caveat in here. Sometimes isolating, I say isolating, and everybody's like, yeah, we've been isolating forever. We now isolate these shear walls, right, because there's openings. This is not what I'm talking about. These are not places where I want to put control joints just because there's an opening there. We're going to get into this in a lot more detail. Shear walls should look like this, from a structural engineering perspective. We can go well past those openings. Maybe we still want to isolate them. We don't want to go too far to have to add more than minimum reinforcement, right? But it's not openings that are going to create those need for control joints. But like I said, we'll talk about that. So I guess movement joints, some three basic factors. All buildings move. CMU shrink and bricks expand, right? So we kind of have buildings moving around vertically, horizontally, lateral loads that are going to be applied on structures, right? We have masonry that doesn't shrink. If you're an engineer, when I say shrink and I say movement, all of a sudden I start correlating it to concrete, and it's not the same. It's not the same minimum reinforcement requirements that you have with concrete. It still has some thermal loads that are similar to concrete, but again, it's a lot less volume. So when I say shrink, I mean shrink, but I don't mean the same thing as when I talk about concrete elements. Bricks, on the other hand, these little gravity-resisting items like to expand vertically and horizontally, right? When I talk about bricks expanding, a lot of times people think, well, that grows, you know, in the plan direction, right? A lot of people that have did a lot of just single-story construction throughout the years, yeah, I mean, that's the only thing that they really had to worry about a lot, but they do expand vertically. And like I said, that's what we really need to concern ourselves with when it comes into those horizontal. You guys feel left out over here? Yeah? No? Okay. I'll talk like this for a little bit. All right, Doc. Sorry. You can't. All right, so movement joints. I mean, we have CMU, we have the backup wall, we have a control joint within the wall, and then it's really kind of a different thing once we get out to the front. You know, expansion joint. I'm not so touchy about it. I think other people get a little bit more touchy about it, but I think it's a good terminology issue that we should consider. Just like the whole relief angle thing, it's really, you need to think about what the joint is doing, how it needs to function, you know, and the purpose for it putting there. They don't need to align. They shouldn't align. I can't think of why they would ever align. Somebody told me once why they thought, but then I forgot about it, so it must not have been too important. But it's usually not something that I think would be good from overall use of the building, right? I mean, it's there's just no purpose in the two of them aligning. The isolation joint, you know, when I was talking about differential supports, I think this is just a really good example. Again, this is a veneer. We're looking at how this would be supported, you know, maybe here by the foundation, right? But then if I get up here over the roof, I mean, it's not going to go all the way down the foundation. I mean, you probably don't have brick all the way going through the roof and the wall system. I mean, it's going to be supported on the roof. So we probably need to have some sort of a joint like that, right? We're trying to isolate that element, go around the window and allow it to move vertically different than our piece that's sitting on the foundation. We can see a few more examples here. So hopefully you guys weren't expecting me to talk about colors. I'm an engineer. I'm kind of colorblind, right? Every time my kids ask or my daughters ask me for a clothing advice, I'm like, are you sure you want this? I mean, I can give you some advice, but it's really not going to help out too much. So in terms of like the color of the joint material, I mean, you're kind of on your own. I can't help you there. But location-wise versus, you know, based on what we're doing structurally, I can help you with that. You know, this is another good example. Again, it's not differential support in terms of you know, one sitting on a foundation, but this is going to just move differently, right? Because it's over this opening. That lintel is going to be moving, especially this kind of cantilevered curved veneer. And I think we need to look for those type of situations in our designs. I mean, if we're creating something that's, you know, aesthetically pleasing and it's got irregularities and it's got some stuff going on here that, you know, this just feels like it's going to move differently, right? I mean, this is just going to be deflecting and twisting and moving, and that lintel is going to be doing something differently than what we're going to have going over just the foundation. So we have to think about that as we're locating those joints. And the movement quiz, I'm going to skip the quiz, but and maybe you guys have probably seen this before, yeah? You guys seen this before? I mean, we have to keep this stuff in mind as we're locating our movement joints in the veneer. All right, a couple more, right? We have stuff going all over the place. So a lot of it, you know, the clay products, certainly the natural stone, which got a little note down there. Sometimes it does, sometimes it doesn't. You know, terracotta tile, brick, all of those things are going to be expanding. As they take on moisture, they're going to just grow over time, and they're never going to come back to the initial place of when the product was made, right? So it's kind of going to be constantly growing over time. All the concrete, cementitious products are going to be shrinking, you know, over time. So it depends on what you use for veneer. A lot of times I'll talk about an expansion joint in a veneer, and that's not necessarily always the case if you got a different veneer material than a clay product. Right, we talk about constructional joint widths, and I think, you know, sometimes, you know, in these seminars we can throw some of these numbers out. I'd be purposeful about this stuff, you guys. I'd put this stuff in your notes or on your drawings, and try to be as specific as possible to make sure that we, you know, sometimes a contractor might say, hey, why is this dimension here? But that at least starts a conversation. I think that's just of the utmost importance, is make sure that we're putting down our design intent as much as possible. Yes, it's going to require a little bit more time as some of these little nuances come in, but it at least creates that conversation. I think that's always very, very important in our designs. And right, in your clay brick is going to be a little bit, you know, wider, because again, that brick's going to expand and going to be filling in that gap. There's some nice little guidelines here for what BIA gives for the distance between where you would need joints and IMI. 20 feet, I think, is kind of a accepted distance that we would have there. And then when we get into the masonry or the backup wall, right, 1.5 times the wall height, not to exceed 25 feet. Some of these are things that I think that are good for most situations, but I like to challenge things, right? If you got in my bio, I'm a software geek. I'm a guy that travels with a bigger technology bag than my overnight bag, right? Everybody's like, you want me to take this bag? It's bigger. I'm like, no, that's my stuff. You can't touch my technology stuff. Take this little bag. It's got all my clothes in. That's not important. What I like to do is I like to take these, what would be kind of industry standard stuff that's been out there, empirical designs, covers a lot of situations, but I like to challenge some of that stuff. Does it really need to be at this distance? Does it really need to be at this distance vertically or horizontally? Let's analyze it. Let's think about it and let's look at it. And we'll talk about that a little bit. But like I said, in the construction documents, we have to be really purposeful. Put those control joints on plans. I've seen, since we created this slide, on plans is kind of the common way to portray the information structurally. In my last 6.5, almost 7 years of being a consultant to IMI, I've actually convinced a few engineers of putting control joints on their elevations of their masonry walls that they did in elevation, which I think is a really good idea, especially if they take to heart some of the things that I'm talking about reinforcing and analyzing and design, being very purposeful about lintel reinforcement and reinforcement within a wall. So I don't think that's a bad idea. So I'll say locate on plans, unless you have an elevation. If I convince you to do that structurally, then put those on the elevations and not on the plans. But yeah, go ahead.
CJs, I presume, are control joints.
Control
MJs
joints.
are movement joints.
Movement joints, yes.
And so that's both
expansion
joints and
yep.
control joints?
Yeah, so the question is, a CJ is a control joint, and MJ is going to be a movement joint that could be an expansion or a contraction, a control joint or an expansion joint. Yeah. Yes. Yeah, I forgot I was in Chicago. I got to clarify MJs, right? You guys got this MJ mentality down here, right? It only means one thing down here. No, go ahead. Yes.
Well, when you draw an elevation and you show where the control joints are, it'd be easier just for the mason to locate the CME.
Yeah, so that's a really good question. So the question is, no, you shouldn't do that. You shouldn't align them. When you do, well, I'll show you why in a little bit. So there's going to be a later part of the seminar that's going to talk about why joints in a veneer should be located in a certain location, why they should be in a completely different location in the backup. So good question. I promise I'll address it. All right, so locating movement joints in specification language or in general notes or even having any notes in there to say anything other than see the plan, see the elevations, right? I mean, if you could put anything in there, don't create a conflict of information. Make sure that you point to the plans or elevations that we're talking about. Corners, sometimes when I talk about corners, looking at the veneers and cracks that you have there, I mean, this is mostly what you want to think about for an unreinforced type of construction or unreinforced masonry movement joint situation, right? So a lot of times we can put on, the plan or have this mentality they should be at 20 feet on center, right? So anytime that you have a plan, right, 20 feet on center, 20 feet on center, going around the corner, right, we have to make sure that we think about, what's going on in the actual corner, right? Because we have too much thermal load that's going to, or moisture and load that's going to be created by those bricks expanding. That's going to be both coming from two different directions here and going to be causing a little bit of cracking there, right? So you can kind of see how both of them are going to be, I really can't pick anything up with the sun, all right? So with both of them growing, you're going to have kind of that opening of the crack in the corners, right? And so especially in this type of situation where you have 24 feet here, 36 feet, 14 feet, we have a lot of stuff going on there movement joint wise. And I think my associate Pat Conway kind of came up with this cute little slide, and I think this makes a lot of sense. You add the distance around the corners. There's a really good way to think about it. I think a lot of times you probably have a shorter distance in one direction. Maybe it's a couple feet in one direction and then maybe close to that 20 feet in the other. So that just prevents that, again, that growing from kind of coming together at a corner and cracking. Right? So situations like this, you want to stay on the near side of the opening, on the far side, because of maybe what you got going on with the veneer and how it's being supported over that opening and how it's going to be able to move. Right? So this is sometimes there's an office standard. That's what I talk about. If you're adding those distances around the corner, sometimes we already have kind of this preset, 2 foot, 2'8" or something like that, that contractors like to use. So it's usually not like 10 feet and 10 feet. It's usually got a shorter distance. And then those inside corners, we've got to make sure that we give our veneers places to move, even when we kind of go inside. The corners, especially, again, we got a couple different products going on here at this cathedral up in La Crosse, Wisconsin. Right? Yeah, and then especially when you get to those acute outside corners, I think that stress can be even easier to show and show some distress with the crack of the corner if we don't have joints nearby. All right, so shelf angles, veneers, and how it affects backups. I think shelf angles, again, not relief angles, are things that certainly you guys need to think about. You need to talk to your structural engineers about what we need in terms of shelf angles. Certainly having those horizontal movement joints, those shelf angles, they're in there to allow the brick to grow so that you can have a gap, at the top of the brick, below the shelf angle so that it can move and grow a little bit and not put undue stress or create this differential movement with the structure behind. So to think about the shelf angles, they certainly are an added cost, right? And so we have to think about that as we're thinking about, well, do we really need them? A lot of times we do, but sometimes, I think that we could start to challenge what's in the code in terms of an empirical design. Functional, liability, gap corrosion, flashing, thermal transfer, all kinds of stuff going on with these shelf angles. And there's a couple of slides in here that kind of show some what I call creative ways to create an offset shelf angle. And I think that those are good ideas for mitigating some of those issues. But I think, again, maybe eliminating them altogether might be the right design for your project. Special brick shape, added cost for special detailing. Again, aesthetic issue, that was definitely not my bullet point. Somebody else put that in there. Aesthetics, I'm an engineer. I don't understand what that word means. All right. So shelf angles over metal studs or over wood construction, right? You guys are all really familiar with this note, right? It's at the height that you can go with brick veneer or with a veneer before you would need a shelf angle is 30 feet. And so how is that number determined? Right? How did they come up with that? What is that? It's based on a bunch of data of existing structures and kind of what worked and what didn't. What height did we start to see some problems with the veneers kind of growing and having some issues with how the veneers are then tied to the backup structure. And again, when we're tying into why are we picking on metal studs and wood, not because the masonry industry doesn't like them. Maybe they don't like them, but that's not the reason why, because it's the reason is, I didn't mean to touch on that sensitive issue, but what I mean is that it's a material that moves. It's an inferior material from a strength perspective, right? Brick is not something that deflects and moves down and shrinks due to its own weight, right? It's something that can withstand its own weight and in fact grows a little bit over time. So it's something that moves vertically up versus the structure behind, especially when it's wood or steel, it's coming down, it's shrinking, it's moving in the opposite direction. When we go beyond 30 feet, we start to have problems with that differential vertical movement, and we start to need to look at different types of fasteners between the veneer and the backup, right? So we start to have issues there because of the structure behind, not because of the brick, right? And so I think that mentality is really, really important. The brick, like I said, can go very, very high. So if it's a CMU backup wall or a concrete backup wall or a different backup wall that's got a similar strength, right, more equally matched, right, more equally matched partner within the design, right, then it's not going to be moving different vertically, and we have to worry about that differential movement. So again, 30 feet, is what we have to deal with when we have those support walls. At gables, we can go up to 38 feet. But what I'm thinking about here is when we have these masonry walls, sometimes people will look at masonry, one, the same as they look at that wood or stud provision, which just doesn't need to be used because, again, that masonry is not moving. It's an equal partner in its vertical movement of the system. So those fasteners and those ties between the two don't have to accommodate a lot of differential movement. So that's really, really important. I mean, if we get into a structure like this one, a 4-story wood structure, no shelf angles, right? As a project built, the brick is certainly fine on its own. We can look at the brick, we can do an analysis of the brick, and I have a couple slides in here for kind of how to do that. But what we have to do is we have to make sure that all the penetrations coming from that wood structure behind going through the brick accommodate for that differential movement. And then all the fasteners between the veneer and the backup have to accommodate for that differential movement. So all those little gaps around all those little penetrations, that's what that's for. That's what that's for, so that that structure behind can, in fact, come down over time due to the occupancy, due to the self-weight of the structure, right? And so then, so that, and again, I have a couple slides here that show some of the analysis. But what do you do when you have a shelf angle? Some of the other challenges were, some of that thermal transfer, some of that stuff. And there's some proprietary products, and I think we might even have some here, or a distributor that can show you some. But just some designed, maybe it's a channel, vertical channel and a horizontal shelf angle, but something to hold off to prevent that thermal transfer. Maybe keep down that angle size so we can keep the leg of that angle within the bed depth of the brick, so it doesn't have to have a really unique look at that joint. Okay, so again, we can eliminate or we can minimize those thermal bridging and delete them by utilizing CMU walls, right? So just the calculation, you guys, the calculation really isn't that bad when we have something else that's behind. I mean, the fasteners and all the stuff that you have to do, I think I'd be an advocate for using similar materials in a backup, in a veneer. But if you wanted to use that inferior one that's going to be shrinking, that's going to be moving, that's going to be coming down as your brick's growing, it's a simple calculation. So when I talk about 30 feet or 38 foot at a gable versus this slide, right? This slide's not that complicated, right? I mean, it's brick movement. There's a few different items that you're going to have to calculate. What is the brick deflection, or what's the delta for your brick due to moisture? What's your delta for your brick due to temperature, right? What's your delta for your brick due to compression, right? That one's kind of funny to calculate because you add the moisture, you add the temperature, and then you deflect or take off the compression, which is pretty minimal, right? It just doesn't move. It's very gravity defiant. It doesn't like to come down. So then you have the structure behind, the structure shortening that you have due to loads of the structure that are on it. And what you have to do is you have to look at the differential between the two. And that tells you the type of anchor that you need, tells you the gaps that you need for the penetrations. I paint kind of a simple picture because it is pretty simple. It's really not that complicated. So when somebody says, do we really have to go 30 feet high and then I have to put a shelf angle because my building is 32 feet? No, not at all. I mean, you maybe want to do this calculation, which would be really simple and fast and easy, but you definitely don't need to put it in there just because it says 30 feet, for those elements. Because it says 30 feet for those elements, unless you want to do a more robust analysis, right? And that's where I really love the again, finite element analysis of these veneers. People are like, you do a finite element analysis for veneers? I'm like, yeah, it's kind of cool. So I'll show you a couple slides in a little bit. So, right, it's just running an analysis of what the structure is going to be doing, moving, deflecting, shrinking, and then doing an analysis, a finite element analysis. I think is a really good way to determine what the overall brick movement would be, right? So it's a project that we helped with recently, right? You guys have seen this. Engineers have showed you guys this, trying to impress you guys, right? Not this one, but this one, right? Colors. No. So, I mean, you can see some of the differential movement that you have, and how the veneer is going to be moving due to some loading that's going to occur on the structure. But it's just not that complicated. It takes a little bit of time. It takes that extra step. I agree. But sometimes, taking that extra step, eliminating those shelf angles, it's going to save a ton, in construction dollars for the shelvings that you have to put in there and all that joint material and stuff like that. So we really want to think about this and think about the types of structures that it would be a good application for, right? So I'm not saying, again, every time I do this, somebody will say, but Sam, it's probably not what you want to say to do at every structure. Don't do this in every structure, right? But you do have this option. You have the option to look at veneers differently. You don't have to go by those empirical methods and just go to 30 feet, stop, put a shelf angle, then move on for the last 3 feet of your building, right? Think about this. It's not that complicated, especially when you're an engineer that likes to do finite element analysis, which none of you are, but you guys all know one, right? Okay. All right, movement joint locations in the CMU or in the backup and how it affects structural capacity, how it changes the in-plane wall design. And again, I'm going to bore you guys with a few numbers just because I think it's really important. I mean, it's trying to convince you to never put a control joint in a structural element, for one, right? And then if you see them in these locations that I say don't put them in by an engineer, make sure you call me so I can call the engineer and have a chat, because it's really affecting the performance of the design in an adverse way. So we want to make sure that we're giving masonry its full due. I mean, it's got a lot of capacity, and we don't want to just add one little joint in one little location that's going to bring down the capacities by 60% or 70%, right? I mean, we want to use the material that we have on site. So putting elevations like this and identifying control joints and where reinforcement goes is really good. It's simple stuff like this, right? And there's not a lot that you're going to see on these slides. Control joints are pretty simple in a structural wall. It's really not going to change your engineer too much, other than again, that in-plane shear capacity. Some of these joints are going to make a difference in how you use them. Some of them have some out of plane shear capacity. A lot of times when I talk about shear capacity, I'm talking about in the plane of the wall, right? This one is a detail that allows make sure that the wall doesn't move out of plane to one another. So for everybody in the other classrooms and everybody online, they have no idea what I'm doing with my hands, but sometimes those walls would have moved a little bit, in this direction. One spanning a lot higher than the other one. Sometimes a key like this is going to be really important to make sure that they don't move differently in the out of plane direction, right? You can do a gasket. You have a couple different options there within your backup wall. Control joints, again, at corners, when I talk about isolating elements, a lot of times going around corners or doing T's, we need to think about how our wall really wants to perform structurally. If we're going to put control joints, if we're going in that direction, we're not eliminating them. I'm going to talk about that in a little bit, but if we are, a lot of times at a corner is a good place, because it keeps the analysis reasonable and the movement of that element reasonable for most walls, right? So we have control joint at the corner. I think that's something that we need to think about when we look at bond beams, because bond beams, if we have a continuous bond beam through control joints, that control joint's just not operating as a control joint. It really does need to have, say, a smooth bar, at the control joint. You need to think about that in your bond beam details, right? At that T-wall, like you could have the little hook that I showed in there before, or a smooth dowel if that's what the contractor prefers. So all things that we have to think about as we look at different details in our design. And again, smooth dowel, I think, is what would be appropriate to allow that wall to move. Other things that affect control joints in a structural wall, when an engineer is designing, say, an in-wall pilaster, right? Those are real things. Those are, we're putting enough reinforcement and grout within that wall to eliminate stuff like steel columns that don't need to be in there, that don't have as much capacity as this anyway. Well, when we do this, we got to make sure that control joint doesn't just fall in here. And so if an engineer is not locating them, how big's that pilaster? Where's the pilaster centered? All of those things are things that an engineer really needs to be a part of. Right? Sometimes we have these larger pilasters. Sometimes those should have control joints. Sometimes they should not, depending on what type of design we're doing here. Again, we want to make sure that it doesn't somehow land within the pilaster. And I think architecturally that would look kind of silly here too. So I think we're all on the same page. That wouldn't make a lot of sense. But coordination required. If for some reason you can't talk your engineer into doing that in plane pilaster, which is a good design, and I'd be glad to talk to him, but in case one slips through the cracks, anytime that we have steel that gets buried within a wall, that's probably a location that you want a control joint, right? Because most likely that steel is not going to fit really well within the masonry, right? And so it's the times in the pictures in the projects that we've seen, masonry face shells and stuff like that shaved down, or anything, big plumbing pipes that go in those walls. Think about control joints at those locations, right? And so looking at control joints, looking at what they need to consider detail-wise, just looking at the capacity. I'm just going to throw a couple examples up here, because I think it's really important. The spacing between control joints is critical. A long wall is going to have a lot more capacity for the in-plane shear design. So what does that mean? The wind that's going to be applied on a building, if I have a really long wall, I'm not going to need a lot of shear walls. I'm not going to need a lot of special reinforcement if I have a few long walls. If I have a bunch of short walls, right, I'm going to need probably all of them because they just have so much less capacity in design. And even in an example of just adding one more joint, right, for the contractors that are trying to be responsible, trying to make sure that they don't have any cracks, and they just throw that one extra joint in there, that can bring down the capacity by 33%. That's quite a bit. I mean, especially when, we have a lot of buildings that have a lot of exterior glazing, windows. We have sometimes all glazing on the outside, right? And sometimes the masonry does get reduced quite a bit, for the what would be there for lateral shear wall. So that one joint might be the difference in a design working or not working. Openings and how they affect structurally, the difference between veneers and structures. So this is probably the biggest part to where with openings, this is why control joints are probably going to all end up in different locations between the veneer and what we have in the backup wall. I think this document is used very well by you guys. It's not used very well by your engineering counterparts. And I really mean that because what this document is really meant for is trying to identify locations within unreinforced masonry that you need a joint. You need a joint in this location because it's unreinforced. I need a joint in this location because it's unreinforced. I need a joint in this location because it's unreinforced, right? So it's got a lot of that information. It doesn't have a lot of information on when it is reinforced. It's got a little, right? It's on the last pages, and sometimes people skip those, right? But it's it gets overused because I think people use this first diagram, this first picture, and engineers are just maybe like little kids. They like pictures and they get attracted to pictures. And this first picture is pretty cool, right? So it shows all of those locations, right? At the window openings, change in height of the wall, pilasters. Maybe we want to have control joints in all those locations, right? All makes sense for an unreinforced design. This looks pretty familiar, right? So what I'm saying is, with a structural wall, whether it's going to be a veneer, whether it's going to be a single white wall, a veneer, a backup to a veneer, or a single white wall or whatever, a structural element, as soon as we start to add reinforcing, that control joint can't go here, right? With the way that it should be reinforced, with the reinforced masonry lintel, right, and a vertical jamb reinforcement, control joint can't go there, or it shouldn't go there, right? So in fact, when I said they overuse that guide, if they go to the last pages of that guide, that's when they see these pictures showing the joints away from the openings, reinforced walls. So that's why they just end up in different locations. So back to that question over here, and I can't there. That's why they end up in different locations. I mean, openings create a completely different scenario for veneers and what you have for backups. And so they don't need to be in the same location, and oftentimes they just don't end up in the same location because of some of the rules that we have here. Within the next guide, and these NCMA tech guides are really, really good. If you guys haven't used them, you should definitely use them. This tech guide is going to be another tech guide that an engineer really should get his hands on because he has a really good understanding for why reinforcement or why control joints are located where they're located. Say that 25 feet or something like that. That can go to 30 feet. That can go to 40 feet. That can go to a lot longer if you want to increase the amount of horizontal joint reinforcement that you have in a wall. A lot of what we have in there is kind of this empirical method of, if I have just common joint reinforcement, this is how far I can go with control joints. Or if I add more reinforcement, then I can go even further, right? And so within the end of this document, it also talks about eliminating control joints altogether. Right? And I know when I bring this up, people are like, oh my God, Sam, you can't talk about this because we added joints back in because, we had problems. And yes, we added joints in because we had problems in masonry when we didn't have a lot of horizontal reinforcement, or we had no reinforcement, right? We had a lot of unreinforced structures historically through time, and that's why we started putting in control joints. Well, it doesn't mean that we can't add enough reinforcement in a masonry wall to not need control joints. When I talked about this in San Francisco, they were like, well, Yeah, but right. So they have a lot of reinforcement in there because it's going to be a wall that is needed seismically to have a lot of the vertical and horizontal reinforcement to make sure that it responds to those seismic loads. And so they just don't need them. They don't need control joints other than to just isolate those structural elements, right? So this is kind of a, this is a given there. And it's just not as common here because we've gotten into this mentality of we need to have control joints. Well, you need to in unreinforced walls, and you need to have them in certain locations for reinforced walls, but those can be moved. They can be changed. They can grow if we increase the reinforcement. If we increase the reinforcement enough, we can eliminate them. And I think that it's just important to think about. I mean, when we get into certain designs, we put in our vertical reinforcement. We have our masonry lintels that are in there, right? You can see all the reinforcement that you have in this wall elevation. I don't need control joints at those openings. Right? I don't need 4 control joints here at every one of those openings. It just isn't needed, won't perform right. The gymnastics that I would have to go through to get them in there, it's costly. It's not worth it. It makes the capacity of this system go way, way down, right? So the control joint locations that are in there for veneers, in that guide for veneers, just don't apply to this, right? And so, like I said, if we switch over from joint reinforcement to horizontal bond beams, I even need less, right? And I probably don't even need those. Right? So it's just thinking about what situation you have. Again, this isn't a one-size-fits-all. This doesn't apply to every design. A lot of common masonry walls should have vertical joints in the Midwest just because we don't have a lot of projects that require all of these bond beams. But this is a good option. This is a very good option for certain designs. And just a couple projects here where we can see those joints getting moved away, and we can see, I think there's a robustness that you can just kind of see in these pictures. When I don't have a joint at an opening, you can just kind of see that it's going to be a lot more rigid if I would push on the structure kind of in the plane of the wall, and it would have a lot of resistance to movement, right? And I think the last one that I'm going to end on here is just, this is a project that we got involved with in the Minnesota Coalition, right? They were looking at putting control joints at every one of these pier locations, right? Because they couldn't go more than 30 feet. So to go to 2 dock doors, they would be 36 feet. That just wasn't going to work for their design, So what do? We take this design, with all those pier locations, and we just eliminate them, right? We take this reinforced masonry lintel, we make it continuous across the top of the openings. We have reinforcement that's going to be at the top of the wall. Right? So we design for that area of that building because it just doesn't make sense to put control joints in here. It's not going to be good for the building use. It's not going to be good architecturally. I think it would look bad again, but I don't have an aesthetic eye, or I end up colorblind, so I don't even know what color's on the screen. But we just don't need them engineering-wise because we have enough horizontal reinforcement. Now, I'm not saying for that building to just then ignore typical construction and control joint rules. For the rest of the building, go back to the typical rules for control joints. That's fine. It's not a once I do this for this elevation, then everything's got to go without control joints. That's not what I'm saying. All right, we're getting close. All right, so loose lintels. People ask me about that. I think those are good. They allow the veneer to kind of work separately and work kind of on a separate set of rules. I think those, as long as it's a reasonable span and it's a reasonable loose lintel angle that we can design. Anytime that we get into fixed lintels, right? We have to attach the lintel to the backup. We have differential vertical support systems that are going on. We have control joints in the backup now that we have to consider in the veneer. So then they maybe have to start matching, like the gentleman on my left that I can't see. I feel like I got in a car accident, right? He's got like one of those head braces. No. So, so it's those fixed lintels do create a new set of rules that you have to consider for your design, for your veneers and your backups, and there's going to have to be a lot more coordination there in your design. Different lintels, so there's going to be the loose lintel, and again, I'm going to pick on the fixed lintel or that steel lintel in a little bit. Loose lintel going behind backer rod and sealant, having the joint going vertically, have it going horizontally, where you have steel there. A little bit on the perforated shear wall, when I'm talking about getting them away, and I'm getting a little short on time, I'm going to flip through a few of these. What I'm just talking about is getting rid of that one joint, right, allows that perforated shear wall to have 3 times the capacity. And this is not a hard analysis to do with finite element analysis, right? And it's very much second nature to me, and it's not second nature to structural engineers that you work with for masonry. It's very much second nature to them for steel, for concrete, for post-tension concrete, for all kinds of designs. So it's familiar to them. They just need to get familiar with masonry and finite element analysis, which isn't that. We just did a course on it in Central Illinois, and I'm sure we're going to do a lot more. It's not that complicated. It definitely is a new material, but it's going to be very similar to what they're dealing with some of those different concrete applications. All right, so just a really quick recap. This control joint, unreinforced, right? That's why it goes to those locations in veneers. This doesn't work when we get into reinforced walls. We want to make sure that those joints get away from the openings when we let the masonry lintels and the masonry jam reinforcement prevent any of those cracks from occurring from those corners, which is what you're trying to eliminate. So since I said that, somebody's going to say, well, Sam, we don't use masonry lintels. Well, and I'm going to come back and we're going to talk about masonry lintels for a full hour, but just a really quick snippet here. Masonry lintels are going to be economical. They match the wall, move the same rate of the wall, build in place, easily 6 to 10 feet. A lot longer spans are certainly possible. In Michigan, there's one that's 27 feet. And I hear stories of 30, 40 feet. Again, we can do a lot with masonry as long as we have the depth to do it. And in most cases, we have the depth to do it in design. When we have masonry lintels, also considering arching action, that's stuff that we inherently get when we look at it with finite element analysis. But even if we're not, arching action occurs when you get those joints away from the openings. And that's something that's really important in design. So again, you can just see this. If I peel apart the face shells and you just kind of look at how that wall is going to be integral, right, with the jams and the lintels and everything that you have there because of the overlapping reinforcement, it's just going to have a much more robust design. Usually the reason people talk about steel lintels is to do with shoring, and we're seeing a lot of contractors moving to prefabricated masonry lintels to eliminate that problem, right? And there's other solutions as well. There's better solutions than putting a piece of steel in there. I mean, it looks better. I mean, this is what it actually is, right? With my X-ray eyes, I'm colorblind, but I can see through walls, right? Anytime I put a piece of steel in there, so I was picking on wood and steel before by saying they're inferior, but I'm just going to say that a steel lintel is it's a foreign material to masonry. And what that means to me as an engineer is it's going to move differently. When it's thermally loaded or when you have different conditions going on, that piece of steel is just going to be moving around and causing problems within your masonry wall. So that one little shoring issue that you maybe solve, you create a lot of other issues in your design. I mean, we can do it. You can certainly put in the reinforcement. You can move over your jam steel. You can add a U-bar in there around the anchor that's going to be in there for the steel. Maybe that's probably going to be in a slotted hole. We're going to try to allow some movement. It's not really going to move too well, so we got to make sure that we reinforce this thing so that it doesn't have problems and we don't have compromised bearing conditions, right? That's not a good word, not a good phrase to use around anybody standing under anything. Compromised bearing. All right, so just in an elevation, you can kind of see that once we have the steel in there, we do have to address it. I've seen some cute details of reinforcing, going through the steel and the coordination and all the stuff that goes on. It's more difficult than it needs to be. It doesn't need the steel, and it doesn't need that control joint, at that steel. And we just have a lot of things that we could resolve by doing a masonry lintel. All right, flip through a couple more of these control joints and stair and elevator shafts. Those are also really, really big deals because I'm telling engineers to use them. I mean, probably the biggest kept secret in design of buildings is all of this untapped capacity in masonry, and no more than in these stair and elevator shafts, right? Because we have them in there, they're robust. They have all these great architectural features that you guys want to use them for, right? Fire resistant and just resistant to abrasion and stuff hitting them, and it's just good elements that you have within the building. And when an engineer doesn't use them, it's just so much capacity. A lot of times we eliminate steel braces in buildings or significantly reduce the amount of perimeter masonry that has to be involved in the lateral support of the structure, right? All kinds of reasons why we want to use these boxed wall groups. And they're really good as long as somebody doesn't add a joint in them. So we got to make sure that, and a lot of times you're not going to do that. They're interior conditions. They're just not going to have a need for putting a joint. But again, I see things sneak into projects where I'm just not sure where they come from, but let's just make sure that they don't end up here because we're using them more. Engineers are realizing this capacity, simplifying your designs, right? When you have that big steel brace, right, that you don't like looking at through your window, right? Ask the engineer, are you using your stair and elevator shafts, right? Your masonry stair and elevator shafts? I'm giving this to you as a gift. Use it, right? So just box wall groups have double the capacity of individual walls, right? Once I start throwing joints in there, all of a sudden it's these individual panels that just don't have nearly the capacity that we would have. I mean, stuff that's 2 to 12 stories tall, I mean, we can easily get these box wall groups that are going to be in there anyway. You're going to have them just due to the use of the building. You don't need to add a lot of or any other lateral support within these designs. So again, control joints, movement joints, and I have a couple slides here on NCMA. It's different between veneers and backup or unreinforced and reinforced wall, right? They just work fundamentally different. They're just different elements that require joints in different locations. Some of them expansion joints, some of them control joints. They affect the structural capacity in those backup walls quite a bit, but it even then also has to do with how do they match up, because they shouldn't align and they don't align. So then we have to have some coordination there anytime that we have a connection to the veneers to the backup. So I agree that it's a complex issue, and we want to just make sure that we understand it. We're not just oversimplifying things to oversimplify them, right? Let the structure do all the work that it can do, right? By not adding these control joints in places that we don't need them. And a lot of the information that I presented to you guys is in these NCMA tech guides. And this presentation is going to be available online. Does Scott usually put his? Yeah. So this one will be a PDF online, and it's live actually on my site if you guys want to go there and see the live one or whatever. But all of this stuff is freely available to you guys. So make sure that you use it. The tech guides are just here within NCMA. This is not stuff that was due to thousands of hours of research for me. I mean, it's using the guides that are in there and then applying the principles in software in finite element analysis. And I know you guys stop saying finite element analysis, but I mean, it's applying the principles that are in these simple guides to the robust tools that you have for structural engineering to get efficient designs. So lots of stuff there for IMI and NCMA. And then, do you guys have any questions? Yeah, go ahead.
It's more of a comment. I'm a mason contractor, and I want to thank you for reiterating that it's up to the architects and engineers to throw the control joints. Because I can't tell you how many times we're being asked to supply shop drawings for control joints. It's in the specification, or we're told to follow some tech note or some guideline. And we push back, and oftentimes the general contractor, they push back on us, and then it ends up being an unnecessary fight, if you will, over whose responsibility is it.
Yeah, so just reiterate, the comment was from a masonry contractor talking about the importance for them to make sure that we have these joints specifically located. Like I said, in your elevations for veneers, in a structural elevation for that structural wall if they're doing elevations, or at least on the structural plans to make sure that we locate them. And it's more complicated than a note. It's not that complicated, but it's more complicated than a note. And there's so much variability between, even they would locate them per, the spec, but then that doesn't necessarily meet your design intent, And so I think that's really, really important that us as designers, that we carry that responsibility through. And it's code mandated. So, other than the code, that's, it's a really good point. Any other questions, comments? So you guys are asking me the questions because I ignored you the whole time, right? Any questions from over here? All right, go ahead.
What's your feeling on lip bricks?
On lip bricks and shelf angles? Gary, do you have a feeling about lip bricks and shelf angles?
Probably necessary. You've got to have them.
Yeah, it's a specialty brick that you're going to have when you have those shelf angles. Again, do you need the shelf angle is a question that I like people to ask themselves. A lot of times the answer is yes, right? I don't want anybody to come away thinking, I don't need any joints any place. This guy's telling me I have, the world that no. We need them in a lot of locations, and we need those specialty bricks due to the shelf angles in our designs. Yeah. Behind me? Oh, you're behind me. Okay, all right. All right, thanks a lot, everybody.
Just a couple of closing comments.
Gary, would you like to introduce your opportunity? Gary Porter from Masonry Advisor
Real
Council.
quick before everybody leaves, there's some handouts downstairs. I don't know if I got enough for everybody, but on December 7th, MAC, Masonry Advisor Council website, and register for this seminar. Down at the East Bank Club, we're going to have two speakers. One of the guys is John Langford. John is here today.